Last week, before we wrote our written response test, we were looking at curved mirrors and specifically on Thursday, the mathematics of curved mirrors. We learned about two equations that we're allowed to use in the context of curved mirrors. They are 1 over f is equal to 1 over do plus 1 over di. We call that the mirror equation. And then the other one, m is equal to hi over ho equals, you got to be careful with this, negative di over do. You can't leave off that negative. That's the magnification equation. Now, along with that, we also learned some sign conventions. When f, the focal length, is positive, when it's negative. When hi, the image height, is positive, when it's negative. When m, the magnification, is positive or negative. Let's go through those sign conventions quickly here, okay? Let's look at focal length first. Okay, focal length, the distance from the mirror to the focal point. When is it going to be positive? When is it going to be negative? About half the time is positive, half the time is negative, right? But which half is positive, which half is negative? Right? Good. It goes with real virtual, right? It's positive if it's a real focal point, but it's a real focal point if it's a converging mirror. And that's the case with lenses that we're going to look at starting in a day or two, a couple days as well. If it's a real focal point, it's going to be a converging lens as well. So you see the word real, positive, okay? And that's going to be converging for the focal point. Of course, you're going to have a negative focal point if it's a virtual focal point. What about the next one? DO. Well, DO is positive when you have a... Yeah, go ahead. It's going to be when you have a real object. And of course, for us, in physics 30, we always have a real object. There are situations, if you go on in physics, where you're not going to have a real object. You could have a virtual object. It could be a negative di, but that's not going to happen in physics 30. So for us, we're always just going to make do a positive value. Finally, di. The last variable in the first equation, di is going to be positive if you have a... Somebody else is going to know the answer to this. Hayden? It's going to be if you have a real image. There's nothing to put in brackets here because half the time you get a real image, half the time you get a virtual image. You just gotta look at the ray diagram, gotta use your head a little bit to determine whether it's a real or virtual image. Okay. Next two variables, I should say. We've got HO and HI. When's HO positive? Not based on real though, is it? Was your hand kind of going up there a little bit? No? All right. Zane, is HO positive or negative? When is HO positive or negative? Good. HO is positive if you have an upright object, which is going to be the case probably 90% of the time, right? If it doesn't say otherwise, you can assume that the object is right side up. And of course, it's going to be negative if the object is upside down. When is HI positive? Tell you, when is HI positive? Good. And that's going to happen, I don't know, half the time. Okay, when it's inverted or upside down, HI is going to be a negative value. And finally, magnification, which doesn't really fit in the table. It kind of goes off to the side here. M is positive when? Not when the object is upright, not when the image is upright, not when the object or the image is real, but rather when the object and image... Good. They're on the same side as of the principal axis. So they're both upright or they're both inverted. But if the object is upright, the image is inverted, it's a negative m. If the object is inverted and the image is upright, then again, it's a negative m. Good? All right, 5 questions for homework. Let's take a look at those 5 questions now. Page 664. Any issues with any of these besides number 5, which I know we're going to have to go over. So we're going to say number 5 right now. Any of the other ones 1 to 4? Yep. 3? Any others? Going once, going twice. All right, number 3 it is. And of course, number 5. 3 says a 5 centimeter high object is placed 2 centimeters from a converging mirror. Now, it doesn't say whether this object is right side up or upside down. But remember what we said. Hey, if it doesn't say otherwise, let's assume that the object is right side up. It's placed 2 centimeters in front of a converging mirror. Okay, I'm going to circle that converging mirror, and I'm going to write a little note here that says F is positive, just to remind me of that. Whenever I see converging, whether it's in the context of mirrors or the context of lenses, as we do in a couple of days, then we're going to make that a positive F. The magnification is -4. Okay, that's a big deal too. Where does the image form, and what is the focal length of the mirror? In other words, we're looking for DI, and we're looking for F. This is going to be HO. This is going to be DO. The magnification is -4. Okay, let's see what we can do here. We get two equations. Look, we got 1 over F is equal to 1 over DO plus 1 over DI. Is that going to help us? Well, we're looking for F, so let's try it. DO is 2. Hey, can we use centimeters there? Is that okay? The units cancel in these equations, right? In both of these equations. If you'd rather convert it to meters because you're used to doing that, then that's fine. But you don't need to in any of these problems involving mirrors. Leave it in centimeters if you want. You just got to be consistent. DI, oh, we don't know what DI is, do we? Okay, so that's not very helpful. Not yet. Okay, let's go to my other equation. M is equal to HI over HO equals -DI over DO. We got HO. We don't have HI. We got M. We have DO. We don't have DI. What do you want to do here? Can't use this equation yet because you have two unknowns. Hey, this one you have two unknowns too, but this one you got two equations, really. Good, good. Let's use the second part of that. M is equal to -DI over DO. Now, don't drop the negative here, okay? DI becomes equal to -M times DO, right? The DO goes up by multiplying. The negative technically comes over by dividing. Comes -M times DO. We get -4 times DO, which is 2, which is -8. Is that right? Is that right? Somebody kind of went, I heard somebody's voice there. Maddie, what's wrong with that? Yeah, I dropped a negative. It's -M. M is -4, so it becomes -4 times 2, which gives me a positive 8 centimeters. Okay, there's DI. Now, it doesn't ask us what the characteristics of this image are, but this tells us something. The fact that we get a -DI tells us that it's what kind of image? Right side up, upside down, real or virtual? Yep. Well, it tells us directly that it's a real image. Okay, it tells us directly that it's a real image, and we know that it's a real image because it's a positive DI. Now, you can work that around using the magnification equation to determine whether it's right side up or upside down. Okay, in the end, it's going to turn out to be, let's see here, DI is positive. It would be inverted, right? Is that what you said? Yeah, it would be inverted. But positive DI doesn't directly tell me that. I've got to put it back into this equation. -8 over 2 tells me that it's upside down. The magnification would have told me that actually, right, without even getting DI there. Okay, let's take that value now and plug it back into here. We got 1 over 2 plus 1 over 8. Now, you can find a common denominator there if you want. It's a pretty easy one to find, right? Common denominator is 8. But just as easy as that is to use that little trick on the calculator. 2x to the -1 plus 8x to the -1 equals, that's not my answer. What do I get to do? What do I have to do to find my answer? Hayden? Put your answer to the -1, which gives me 1.6. So we're going to say F is 1.6 centimeters. Hey, in the end, we didn't need to know that F was a positive value, but what did we get for F when we solved for it? Positive 1.6. So it's still a nice little check. If we get a negative 1.6, we know we've done something wrong because we can see right in the question that it's converging here. Who asked me for that one? Is that good? All right, number 5. Light from a distant planet is incident on a converging mirror. The image of the planet forms on a screen 45 centimeters from the vertex of the mirror. Find the focal length of the mirror and the image characteristics. We don't seem to have very much information there, do we? I'll tell you what. We have something. It says the image is formed on the screen 45 centimeters from the vertex of the mirror. We have DI, right? And it's formed on a screen, so that means that DI it's a real image if it's formed on a screen. Therefore, we're going to make DI positive 45 centimeters. Agree? That's it, isn't it? Anything else? Yeah. Okay. So it's a good point, Rucker. So you got light from this planet really, really far away, and light's coming off of this planet in every which direction, right? So Rucker says something about the rays being parallel. Okay, how do we assume that the rays coming off of this planet are parallel when in the end this planet is reflecting rays in every which direction? Okay. Good. So here's your concave or your converging mirror. Here's your planet right here, really close by. Okay, there's lots of rays coming off of that planet. Some of those rays don't even hit the mirror, right? But some of them do. Those middle 4 rays hit the mirror. Those aren't parallel, right? They're not even close to being parallel. Hey, these ones don't matter because they're not even hitting the mirror. They're there, but they're not hitting the mirror. The only ones you care about are the ones that actually hit the mirror, but they're not parallel. Let's take that back a ways, though. Let's take that object back, way back here. There's all kinds of rays that are coming off of it in every which direction. Most of them don't even hit the mirror. Okay, they miss the mirror completely. Look, that one hits the mirror. That one hits the mirror. That one hits the mirror. Let's erase all these ones that don't hit the mirror. The ones that hit the mirror, you can see, aren't completely parallel, but they're a lot closer to being parallel than the first diagram I drew, right? If I brought it back even further, then these rays would be even closer to being parallel. Okay, when you bring it back the distance of a planet, the rays that actually strike this little mirror are going to be ridiculously close to being parallel. That means they're all going to converge or pretty darn close to the focal point. So if DI is 45 centimeters, then the focal length is going to be 45 centimeters as well. Make sense? Okay, now that's using some logic. Okay, that's great. Okay, I like the way you solved that, Rucker. Okay, there is another way to do it mathematically as well. Let's take a look at our equation. 1 over F is equal to 1 over DO plus 1 over DI. 1 over F. Okay, we don't know what F is. Okay, pretend we don't know what F is yet. We're solving for that. What's 1 over DO? It's DO. If we're talking about the planet that's really, really far off, then we're talking about a really, really big DO. How big is it? I don't know, but it's really big. If it's 1 centimeter away, then 1 over 1 is 1. If it's 10 centimeters away, then 1 over 10 is 0.1. If it's 100 centimeters away, it's 0.01. Okay, that's a meter. How far is this planet away? It's a long way away. As DO keeps getting bigger and bigger and bigger, 1 over DO keeps getting smaller and smaller and smaller. If we're talking about a planet, okay, where DO is going to be, millions of kilometers away, then what's 1 over DO really going to be? Effectively, 0. Yeah. 1 over a really big number is equal to a really small number, which is basically 0. Plus 1 over DI, 1 over 45. Well, would you look at that? Okay, F has got to be 45 centimeters, right? Make sense? What about the characteristics? Well, the first characteristic, or one of the 3 characteristics, I guess it was the third one that we usually list. Doesn't matter what order you do them in, though. It's real. We know that right away. How do you know it's real? Yeah. Good. Images formed on a screen. Okay, we don't know what, we're not told whether it's a positive DI or a negative DI, but in the end, it says it's an image formed on the screen, so you know you're going to make DI a positive value. Good. What else? Right side up, upside down, bigger, smaller. Yep. Okay, so you're kind of thinking of the ray diagrams we drew. When you drew the object farther away than the focal point, farther away than 2F or the center of curvature, and then it formed a smaller image. Okay, that's good logic. We can also get the same answer mathematically. We can say M is equal to negative DI over DO. DI, we said was 45, and DO was, DO is not 0. DO is really big, right? Which makes M pretty much 0, right? Okay. I'm going to just call that infinity. It's not really infinity, but it makes M negative really small, right? Negative really small. So it's a smaller image. And then finally, right side up or upside down. It's not just really small. It's negative really small. So it means it's upside down relative to the object, okay? Rucker? Yeah. Yeah, no, that's a good point too. Just again, not mathematics, whatever, just logic, right? You're seeing the image of a planet on a screen. If you can see the whole planet on the screen, then the image has got to be really, really small compared to the object because the planet is bigger than the screen. If you're seeing the whole planet on the screen, then the image has got to be smaller than the actual planet. Get it? All kinds of ways to answer this question. Funny though, we get a question where there's all kinds of ways to answer it, but yet it's the hardest question on the page. Okay, and if you struggled with the question, I completely understand because, hey, if I was in grade 12, I probably would have struggled with it too. Make sense now, though? All right. I'm going to assign right now for you guys a little bit of homework here. We'll try to find you guys a little bit of time towards the end of class to work on this stuff. No promises, but we're going to assign page 664. Page 665. Some check and reflect questions. Number 4, 5, 7, and 11. 4 questions there. And in addition to that, I'm going to assign worksheet number 16, which is on lenses.